Nearly every exercise physiology, kinesiology, and biomechanics textbook describes the calves as part of a second-class lever system. They're all wrong, and I'm going to tell you why. I'm Matt Fish, and we're going to discuss the calves as part of a first-class lever system with an axis at the ankle joint, and as part of a second-class lever system with an axis at the MTP joints. There are a lot of myths in virtually every textbook that I have seen and all over the internet. So we're going to see if the calves can in fact be accurately described as part of a second-class lever system. Let's go over lever system classifications. We have first class, second class, and third class levers. With the first class lever system, we have a resistance force and effort force on opposite sides of a fulcrum or axis, and either one could have mechanical advantage depending on how far it is from the axis. A second class lever system has the resistance force and effort force both on the same sides of the axis, and by definition, the effort force is farther from the axis and has mechanical advantage over the resistance force. The third class lever system has both forces on the same sides of the axis or fulcrum, but by definition the resistance force has a greater moment arm than the effort force, and thus the resistance force has mechanical advantage. So here's an example of a first class lever. We see the effort force on the left of the axis pushing up and the resistance force on the right side of the axis pushing up, but the effort force is attempting to create a clockwise rotation and the resistance force is attempting to create a counterclockwise rotation. And then for comparison, we have the ankle joint and a resistance force pushing through the heads of the metatarsals, an effort force pulling through the Achilles, and the axis is through the ankle joint. In a second class lever system, the effort force and resistance force are on the same side of the fulcrum, and the effort force by definition is further away and has a greater moment arm. So we have an example of a standard second class lever system compared to the Gastrocnemius and Soleus, compared to the resistance force of body weight and a fulcrum at the MTP joints. Here we have a couple examples of the calves represented as part of a second class lever system. On the left is from the Human Kinetics blog. We have the calves as the effort force, then body weight, and the axis at the metatarsal phalangeal joint. And the force of the calves always has a greater distance or greater moment arm than the body weight compared to that axis, which would make it a second class lever system. And then we have a similar diagram from Visible Body, which is an excellent 3D anatomy software system, so I do actually highly recommend it. And then we have the fulcrum again at the same place. The load from body weights shown a little bit differently, actually closer to the heel, and then the effort from the calves pointing up, but still giving the calves the mechanical advantage, making it a second class lever system. Here's another example. This is from the Essentials of Strength Training and Conditioning textbook, and we have the calves as the effort force. And this time we have the body weight going through the ankle joint and the axis again at the MTP joints. And it says, due to its mechanical advantage, the required muscle force is smaller than the resistance force. This is an image from another textbook, Kinesiology of the Musculoskeletal System, Foundations for Rehabilitation. It states, acting as a second-class lever with the pivot point at the metatarsal phalangeal joints, the gastrocnemius lifts the body using mechanics similar to those of a person lifting a large load with a wheelbarrow. And wheelbarrows are a classic second-class lever system. It goes on to say that if the gastrocnemius functions with a mechanical advantage of 3-to-1, the muscle needs to produce a force of only 1/3 or 33% of body weight to support the plantar flex position. And then on the right we have the part of the diagram that shows the line of force of the gastrocnemius, and it has the momentarm to both the talocrural joint axis, which is the ankle joint, and the MTP axis. And then we can see the line of gravity of body weight just posterior to that MTP axis, and we can see the very short momentarm there. Before we get into analysis, we're going to do a very short fundamental review for force and torque. So force is simply mass times acceleration. We have 3 examples using a single resistance force and a single effort force. If the effort force and resistance force are equal, the total force is actually going to be 0, meaning there is no acceleration. It would be moving at a steady speed in a straight line, or it would be static. If the resistance force was greater than the effort force, it would be accelerating downward. And if the effort force was greater than the resistance force, it would be accelerating upward. Before we move on to analyses, we're going to establish some definitions and review torque. A lever is a rigid body that can move about an axis with one or more forces acting upon it. In biomechanics, they typically refer to bones as rigid levers that move around axes at the joints. However, this is not a useful definition when you're doing a torque analysis. So our definition of a lever is going to be the distance between an axis and the application of a line of force. Our next definition is for momentarm, which is the distance equal to the sine of the angle between the line of force and the lever multiplied by the length of the lever. This is also known as the radius or the lever arm. And we should know that some sources also define lever as synonymous with momentarm, so you have to be careful if you're reading from different sources. Torque is defined as force times the momentarm, and it is also defined as the moment of inertia times angular acceleration. For conceptual purposes, the moment of inertia is an object's resistance to angular acceleration due to the mass, shape, and location of the axis, and angular acceleration is the change in rotational speed or direction. Mechanical advantage is the ratio of momentarm of one force to the momentarm of the opposing force. The force with the greatest momentarm has mechanical advantage. And finally, the sign convention when analyzing torque: counterclockwise is positive and clockwise is negative. In this example, we have an effort force coming from the calves, designated F sub E, acting on a lever designated L sub E, and the angle between the two is alpha. For resistance, we have the ground reaction force, designated F sub R. The lever is L sub R, and the angle between the two is beta. We want the torque from the effort and the torque from the resistance to actually equal 0 in our case, because we are going to do static analyses. True biomechanical assessment is very complex, so here are some clarifications, assumptions, and simplifications. We are assessing right and left sides together. Torque and force calculations will be for both legs combined. We are assessing torque from the primary plantar flexors and the force transferred through the Achilles tendon. The ground reaction force runs directly through the axes of the MTP joints. The contact forces at the tali run directly through the axes of the ankle joints. And finally, the forces that we calculate are the components of forces directly through the tendon. Because all muscle fibers are not completely parallel to the tendon, the actual force the muscles produce will be greater. Our problem setup is as follows. The subject has a height of 200 centimeters. The distance from the ankle to the center of mass is 105 centimeters. The mass is 79.94 kilograms, which gives us a body weight of about 784 newtons, or approximately 176 pounds. They have a forward lean of about 3.4 degrees, and that is to get the line of gravity over the base of support. This diagram is similar to what you would see in a textbook or online. We have the line of force of gravity somewhere between the MTP joints and the ankle joint. Problem number 1 is the line of gravity is outside the base of support and the person is falling over backward. Problem number 2, this is a distal segment analysis, in our example the foot, which means we're only looking at forces of gravity and contact forces. So we would actually look at the ground reaction force. Technically we would look at the weight of the foot, although we can ignore that for simplicity. And we would have the contact force of body weight going through the talus. And finally we have the force of the gastroc and soleus through the Achilles tendon. This diagram shows us our dimensions and our starting weight of 784 newtons. We are ignoring the weight of the foot, therefore our ground reaction force and the contact force of the tibia on the talus are both going to be 784 newtons. For our first analysis, we'll use the classic second class lever system setup, and we will ignore the weight of the foot. We can calculate the moment arms, and we'll find that the ground reaction force has a moment arm of 0. And we can calculate the mechanical advantage, which gives the muscle's mechanical advantage of approximately 2.5 to 1. If we balance the torque, we get a muscle force of about 315.6 newtons, which is approximately equal to 70.95 pounds. And you can see that the torque in each direction is 4,795 newton centimeters. If we add them together, we get 0. Our next analysis will be as a first-class lever system with an axis at the ankle joint. When we calculate moment arms, we see that the contact force, labeled F sub y, is going to be 0. And the muscles will have an approximate mechanical advantage of 1.13 to 1. When we balance the torque to calculate the muscle force, we get 695.6 newtons, and the balanced torque is 4,795 newton centimeters in each direction, which totals to 0. If we compare our analyses, we can immediately see that something does not add up. We have 784 pounds of body weight and the same joint position, so we should calculate the same muscle force. We can see that the torque balances out in each equation, and each equation or each analysis calculates the same amount of torque, but we get radically different forces for the plantar flexors. In fact, we have more than double the force required with the first class lever analysis versus the second class lever analysis. So where did we go wrong? For our more detailed analysis, we will look at the weight of the foot, although we'll see that has minimal impact on the overall torque, and we'll look at the specific force components of the tibia on the talus. We'll have a vertical force component in the y direction and a horizontal force component in the x direction. All of the dimensions and body weight will be the same as before. In this more detailed analysis, we'll look at the axis of the ankle joint. This is similar to a first-class lever system, although we do have more than two opposing forces. The contact forces, F sub y and F sub x, are going to run through the axis, so they have moment arms of 0. If we look at the ground reaction force, that's attempting to push the foot in a counterclockwise direction. The muscle force and weight of the foot are trying to pull the foot in a clockwise direction. When we do the calculation, we get 690.2 newtons of muscle force required to maintain a static position. Our next detailed analysis will be considered a second-class lever system, although we do have more than two opposing forces. This time we have three unknowns. We have the unknown contact force of the tibia on talus in the y direction and in the x direction, and we do not know the muscle force. So we need to create three equations so we can balance all of the forces in the y direction, we can balance all the forces in the x direction, and balance the torque. And then we can actually solve the problem. We are going to solve the moment arms now for convenience, and then we can also write relative values for F sub y, the y component of the contact force of the tibia on talus, and an equivalent equation for the contact force in the x direction. To continue our calculation, we're going to look at equation 3, which is the torque equation, and we'll plug in the equivalent values of the y component and x component of the contact force of tibia on talus. When we complete the calculation, we get a muscle force of 690.2 newtons, and we can also see that the torque in each direction is 10,488 newton centimeters. If we add those together, we get 0. Again, this is what we need for a static analysis. Let's take a closer look at the contact force of the tibia on the talus. We're doing a static analysis, which means the sum of our linear forces must equal 0, just like the sum of our torques must equal 0. If we do the calculation, we'll find the vertical component of the contact force is equal to 1,444 newtons and is directed downward. And our x component is directed to the left at 119.8 newtons. We can actually calculate the total contact force, which would be 1,449 newtons, and at an angle of 4.74 degrees clockwise from vertical. And this is nearly double the subject's body weight, which is the force that is usually used in the textbooks when they're using this type of diagram. All our previous assessments were of the distal segment, in other words, the foot. So we'll do one assessment of the proximal segment, the rest of the body. This is a classic first-class lever system. We have a lever from the center of mass to the ankle joint, and a line of gravity going straight down. The angle between the lever and the line of gravity is 3.4005 degrees. And the weight of the body, not including the foot, is 764 newtons. We can use the moment arm we previously calculated for the muscle force, and we calculate a required muscle force of 690.2 newtons. If we compare our analyses, we can see that the torque can vary depending on what axis we are assessing, and that is just fine. But our muscle force should always come out the same. And this gives us a glaring discrepancy of the simplified second-class lever system analysis, which is the example we see in most textbooks. If we look at the simplified first-class lever that ignores the weight of the foot, we actually get a pretty good estimation for the required muscle force of 695.5 newtons. And if we look at the three more detailed analyses, the first-class lever system with the axis at the ankle, the second-class lever system with the axis at the MTP joint, and the proximal segment analysis with the axis at the ankle joints, we get a required muscle force of 690.2 newtons for each one. This example is going to illustrate the reversal of mechanical advantage. The moment arm of the muscles used here is an average from looking at several studies, and it does change very, very slightly throughout the range of motion, but I did find some studies that say the moment arm can increase very slightly, and other studies said that it can decrease very slightly throughout the full range of plantar flexion. And then I also used nice, easy numbers to give me good ratios. So, for example, as you begin, you're going to have a greater moment arm for the ground reaction force than the muscles. The ground reaction force in this example has a mechanical advantage of 2-to-1. As we start to move through the range of motion, that mechanical advantage gets less and less. And we have a 3-to-2 mechanical advantage at approximately 30 degrees plantar flexion. And then finally, as we near end range, or about 50 degrees of plantar flexion, the muscles actually achieve a 3-to-2 mechanical advantage. Let's revisit the diagram from the Essentials of Strength Training and Conditioning. First thing you should notice now is that the person is falling over. The base of support is between the heads of the metatarsals and the toes, and the line of gravity shown in yellow is clearly behind the base of support, so they are in the process of falling over. 2, they have the correct placement of the primary resistance, meaning the contact force of the tibia on the talus, but this is not equal to body weight, and the muscle will have to produce far more force than body weight in order to create plantar flexion in this position. And then finally, the gastrocnemius and soleus are best described as a first-class lever system and can be at a mechanical advantage or disadvantage at various points within the range of motion. Here is the diagram from the Kinesiology of the Musculoskeletal System textbook. First thing we should notice again is the person is also falling over, although the line of force of body weight is extremely close to the base of support. Another thing we notice in the diagram is it shows the axis of the ankle and the MTP joints. That's fine for a general diagram, but not for analysis. If you're going to do an analysis, the moment arms of the resistance and effort must be compared to the same axis. And then finally, the gastrocnemius and soleus are best described as a first-class lever that can be at a mechanical advantage or disadvantage at various points within the range of motion. We have the example above where if the gastrocnemius has a mechanical advantage of 3-to-1, it only needs to produce a force of 1/3 of body weight. And that statement in and of itself is true, but it's going to be very, very difficult for it to get a mechanical advantage of 3-to-1. This is not meant to be a critique of either textbook. Both are excellent sources of information, and the Essentials is probably the most popular textbook specific to strength and conditioning. And the Newman book is actually my favorite kinesiology book on the topic of rehabilitation. Just because there's a few things I may not agree with does not mean they're not reliable sources of information. You try writing a 700-page textbook and see if everyone agrees with what you said. In conclusion, I'd like to go over 4 main points. 1, the concepts of first class, second class, and third class lever systems are useful when learning about torque, but very limited when looking at more complex systems. 2, the concept of mechanical advantage is far more versatile. If you have multiple effort forces and multiple resistance forces, you can still find the average moment arm of all effort forces and the average moment arm of all resistance forces to find the mechanical advantage. 3, if using a simplified analysis of the calves, they're best described as part of a first-class lever system with an axis at the ankle joints, and they can be at a mechanical advantage or disadvantage at different points throughout the range of motion. And 4, the calves can be analyzed as part of a modified second-class lever system with an axis at the MTP joints. However, they will often have to produce more force than body weight, and this is because the true resistance force with that analysis is the contact force of the tibia on the talus, which will be greater than body weight. I hope this was helpful. Thank you for watching, and please leave your questions and comments below.